Dear students, the topic of this video is physical significances of wave function. And first, I will discuss about the wave function. What is wave function? We know that for propagation of wave, we require a fluctuating periodic parameter. Suppose propagation of a water wave, the heights of surface of water is periodically variable, and similarly for propagation of sound wave, the pressure of the medium is periodically variable, and for propagation of electromagnetic wave, electromagnetic field is variable, periodically variable, and similarly we require a physical parameter which should be periodically variable for matter wave. For propagation of matter wave, we require a physical parameter which is periodically fluctuating, and that is known as wave function, and it is represented by psi. And first physical significance of wave function is psi must be continuous and single valued everywhere. This is first physical significance of wave function. Psi must be continuous and single valued everywhere. And similarly, differentiation of psi, del psi upon del x with respect to x, or differentiation of psi with respect to y, differentiation of psi with respect to z, del psi upon del z, also must be continuous and single valued everywhere. This is second physical significance. And third, psi must be a complex number like psi equal to a plus ib, where this part represents the real number and this part represents the imaginary number. And for complex number, we know that conjugate of this complex number we can represent it by a minus ib, and we know that psi star, we can write it psi square. It should be equal to a plus ib into a minus ib, or we can write a square minus ib square. I square is minus 1, minus plus, we can write it a square plus b square. Psi star or psi square, it should be equal to a square plus b square. This psi square, number 4, this psi square represents the probability of finding the particle. Probability of finding the particle at a particular time and at a particular place. This is the probability of finding the particle, and this is fourth physical significance of the wave function. Now we move towards the fifth physical significance. Number 5 is we can represent psi as a e to the power minus I h minus I omega t minus x upon v. This is the value of psi, and we can also write psi equal to a e to the power minus I upon h cross et minus px, where E is energy of particle and P is linear momentum of the particle, and this h cross we can represent it by h upon 2 pi. This is the value of psi, and number 6, integration x1 to x2 psi star dx, and we can also write it x1 to x2 psi square dx represents the probability of finding the particle from this limit x1 to x2, from x1 to x2. This is the probability of finding the particle within this limit x1 to x2. And next physical significance is minus infinity to plus infinity psi square dv, where dv represents the three-dimensional dx, dy, dz. If it is equal to 1, then this condition is known as normalization. This is normalization if minus infinity to plus infinity limit psi square dv, that it is equal to 1. And to correlate the theoretical and experimental relation, we define the expectation value, and we can also determine the expectation value that should be minus infinity to plus infinity. By the help of this term, we can determine the expectation value of x psi square dx. This is the expectation value of x. This is we have to require to correlate the experimental and theoretical data. So these are the physical significances of wave function, which are very important in wave mechanics, or we can say quantum mechanics, or modern physics. And thank you. And in next lecture I will discuss about the Davison-Germer experiment, which is the first experiment in which we have proved about the dual nature of the electron. Thank you.